In this video, we are going to be finishing up the topics for chapter 21. We are first going to discuss the concept of conjugated addition reactions. As you can see, we first, in the beginning of this chapter, learn about alpha-beta unsaturated carbonyls that are made via aldol condensations. So when we have an aldehyde, as you can see in the first reaction, here marked with a check mark, we have an aldehyde that is going to react with itself. And when that occurs, remember that depending on the conditions that we have, we can actually generate an alpha-beta unsaturated carbonyl system that in this case is going to be an aldehyde. So at the alpha position and at the beta position from the carbonyl, we're going to have a carbon-carbon double bond. Now, understand that this alpha-beta unsaturated carbonyl has 3 resonance contributors, and they are outlined in the bottom of the slide. So, overall, as you can see in the gray box that is shaded on the top of the slide, the 3 different resonance contributors to the alpha-beta unsaturated carbonyl represents that there are going to be several positions where we are going to have a partial positive side along with some partial negative charges. So understand that overall, at the centers in which we have the carbon in the carbonyl, in the carbon that is beta to the carbonyl, those are going to have partial positive. What that means is that those 2 positions are going to have electrophilic ability. So when we have reactions occurring to these systems, understand that the points of attachment will be, and specifically those 2 sites that have that partial positive side or partial positive symbol. So when it comes to these type of reactions, the first one that we are going to be discussing is called a 1-2 addition. Okay? So in a 1-2 addition, you have to think about that if I label the positions in that alpha beta system, this is position 1, 2, 3, 4. So the chemistries that we are going to be discussing at this moment is going to be at 1, 2, which you can see that I highlighted those atoms in green. So the first reaction that we're going to talk about is the presence of Grignard reagents attacking that alpha-beta carbonyl system. So when a Grignard reagent is attacking this alpha-beta system, they undergo a 1-2 addition. So what that means is that specifically the R group that is part of the Grignard is going to be attaching to carbon 2 or carbon labeled number 2 in our original molecule. Okay, because remember that these labels are generic. So the carbon atom that is labeled number 2 is the one that is going to bind to the R group, and after the acidic workup, as you can see, the oxygen atom is going to turn into a hydroxyl. Now, we have another set of reagents that are actually called Gilman reagents. And when we have a Gilman reagent, understand that they generally attack the beta position. So if the group that you're trying to incorporate, the alkyl aryl group that you're trying to incorporate, it's at the 4 position, and again, if I use the same numbering that I utilize in the first molecule, where this is atom 1, atom 2, atom 3, and atom 4, the Gilman reagents are going to add specifically 1, 4, and as you can see that I highlighted the atoms. And this is just utilizing showing that we are adding at the beta carbon from the carbonyl. The Gilman reagents are very specific because, as you can see, your R group is going to be bonded to copper and lithium. You're also going to have an acidic workup, but understand that in this addition, this 1,4 addition, we are going to regenerate our aldehyde. Let's talk about the general mechanism for a conjugate addition. Okay, so when it comes to these reactions, as you can see, the nucleophile is going to add specifically to the carbon that is beta. Then the electrons between beta and alpha are going to move between the alpha carbon and the carbon in the carbonyl. And as you can see, this is going to form an enolate. This enolate is going to be then protonated in the acidic workup, and that's going to result into the formation of the enol. Once that enol is generated, then through the process of tautomerization, that's how we generate the aldehyde at the end of the day. And again, this mechanism is the one that it is visualized for that Gilman reagent reaction in the 1,4 addition for the alpha beta unsaturated carbonyl systems. Understand that strong nucleophiles tend towards the 1,2 addition. Less reactive nucleophiles tend to do conjugate additions. So understand that the typical enolate often gives a mixture of 1,2 and 1,4 addition products. Okay. Now, if you have a stabilized enolate, they are going to be specifically giving you the 1,4 addition, as you can see in the example that we have below. So in the example that we have here in the reaction shown in the bottom of the slide, what we have is that in the first step of the reaction, when we react this dicarbonyl system, we are going to be deprotonating. So this base is going to deprotonate, i.e. making an enolate. Once that enolate is going to be formed, then, as you can see, we're going to have the addition of that enolate, specifically at the carbon atom that is at position 4 from the oxygen and the carbonyl. Okay, and then in the acidic workup, understand that that enol is going to tautomerize to the aldehyde. So this is just illustrating specifically an example of a stabilized enolate. Now, understand that this 1,4 addition that was presented in the previous slide is actually called a Michael reaction. And in a Michael reaction, we're going to have two components, a Michael donor and a Michael acceptor. The Michael donor is going to be the nucleophile that does the conjugate addition, and the Michael acceptor is going to be the alpha beta unsaturated carbonyl system that is going to be making the new bond with that Michael donor. So in your textbook, in table 21.2, we have a list of common Michael donors and Michael acceptors. Okay, so as you can observe here, these Michael donors are going to be acting as a nucleophile. And as you can see, for every single one of the examples that we have for Michael acceptors, remember that the addition, okay, meaning the bonds that we're going to be formed, is specifically where we have those delta plus sites, which is the position 4. Remember that when it comes to this, atom 1 is going to be your oxygen, and then you're going to number towards the alpha beta unsaturated system. So where we have those delta positives, that's position 4 in the system. Understand that because singly stabilized enolates do not give high yielding Michael addition, we also have a reaction that is called the Gilbert synthesis. Okay, so this specifically utilizes an enamine intermediate in order to have the reaction work. Okay, so I hope that from section 19 you guys remember how an enamine is formed. As you can see, an enamine is formed where we have a ketone that reacts with an amine, and that's what forms specifically the enamine molecule. Enamines behave like enolates. In other words, they are nucleophiles. And as you can see in the slide, we are just illustrating how an enolate and an enamine look similarly in terms of the carbon that is alpha to the double bonded atom. In the case of the enolate, is to oxygen. In the case of the nitrogen, in the case of the enamine is to nitrogen, we can see at the alpha position that negatively charged atom, which is carbon. Okay, so understand that enamines are next nucleophilic, but they can be considered a Michael donor. So as you can see, if we have an enamine present, they can undergo this 1,4 addition into alpha beta unsaturated systems. Understand that after the conjugate addition and the use of aqueous acid is going to specifically convert groups into carbonyl. So you lose the double bond nitrogen, so that iminium group is going to turn into a ketone, specifically in this example. And again, the enolate is going to overall tautomerize to the ketone just because of the starting material that we have, specifically in our Michael acceptor. So understand that if we look overall at the Stork enamine synthesis is a 3-part process. You start with the ketone, and that ketone in the first step of the reaction forms the enamine. In the second step of the reaction is where the enamine acts as a Michael donor, and it adds at the position 4. Remember that this position 4 is not carbon 4, is just labeled that way because we're counting the atoms from the double bond oxygen in our alpha beta carbonyl system. Then in the third step of the reaction, as you can see, we're going to have the hydrolysis step, in which the component of our alpha beta unsaturated system and what used to be the double bond nitrogen in the enamine, they both are going to turn into carbonyl systems. The last set of reactions that we are going to be looking at is going to be Robinson annulation. And understand that Robinson annulation is going to be specifically a 2-step process for forming a ring, in which specifically we're going to have first a Michael addition, then we're going to have an intramolecular aldol condensation. So as you can see, all of the mechanism for Robinson annulation have been discussed in this chapter previously. That's why we don't have it illustrated step by step. My suggestion will be that you try to outline all those steps on your own, because you have been demonstrated part by part how to do this mechanism. So let's get started. In the first part of this process, as you can see specifically, we are going to have a Michael addition, in which the molecule on the left is going to be the donor, the molecule on the right is going to be the acceptor. So in the presence of an AOH, because we have an activated molecule, it's in a way stabilized by that double C double bond O, we are going to create the Michael addition. So we are going to bond specifically to this delta plus area, which I'm highlighted in green, from donor to acceptor. So as you can see, this represents step 1. Once that has occurred, understand that overall what's happening here is that within these two systems, in the presence of an AOH, what's going to be occurring is that once we heat up this system, we are going to have this area and this area of our ring system cyclize to give rise to this alpha beta unsaturated system. So that's part of the aldol condensation. As I mentioned before, this is a mechanism that I would like you to try at home to demonstrate how the Robinson annulation process actually occurs. So understand that in this chapter, most of the reactions are carbon-carbon forming reactions, okay? And they also yield products that contain at least 2 functional groups. We talked about aldol reactions and aldol condensations, Claisen condensations, and stored enamine synthesis, okay? Which is part of the Michael reactions. So understand that the positions of the functional groups in the target compounds are going to be dictating the reactions that can be used to synthesize. So the reactions in this chapter is mainly for synthetic strategies. So, as you can see, if the stored enamine synthesis is going to be utilized, that's because we are going to be forming compounds in which we have a 1,5-dicarbonyl compound. If the product of our reaction is a 1,3-difunctional compound, most likely we utilize aldol or Claisen strategies in order to form them. So this is just to give you a clue of what to look out in general. Also, when it comes to other strategies that were outlined in this chapter, you guys have learned 2 methods of alkylation. The methods of alkylation, number 1, is at the alpha position of the enolate. It can actually attack an alkyl halide, and that's how an R group can be incorporated into the system. And then we also have the Michael donor that can attack at the beta position of the Michael acceptor in order to create that new carbon-carbon bond, okay? Understand that these 2 can also be combined. What that means is that if we look at this system specifically, and we look at the example of the reaction that I'm marking with a check mark right here, in reaction number 1, as you can see, we have a Gilman reagent. And then that Gilman reagent, specifically what it's doing is that is adding at position 4, in other words, the beta carbon, into the system. That's where we see the incorporation of the ethyl group. In step 2, remember that if you don't do an acidic workup in this system, what you can do is introduce an alkyl halide and do inoculation at the alpha carbon. So this is just illustrating how these reactions can work side by side.